Agency. Okay, so as you can see from that message, we've just started recording as well. If any of you are not okay with that, let us know immediately. Okay, so that clap there is for our general sponsors. And obviously, we also have affiliated organizations, mainly the organizations that the workshop organizers come from. So feel free to interact with everyone asynchronously on the chat window. Some of us will be monitoring the chat windows. Anytime at all, feel free to type something in the chat window if you have questions or comments. This is the program for the whole workshop. We've done block A yesterday, at least yesterday in my case. And today we're going to do block B, which is this one right here. So at the end of the block, we have the award announcements, and we'll be announcing 3 awards: Best Paper Finalist Award. Actually, we've announced those yesterday, the Best Paper and Best Paper Finalist Award. Most of you probably don't know who they are yet, so it's still going to come as a surprise. And we'll also announce Best Presentation Award for Block B. So this is based on today's performance for the papers who'll be presenting at the spotlight. Okay, so try your best for the spotlight because you might get an award. Okay, the other highlight besides our invited speakers are as well for the paper presenters. We have the spotlight sessions where you'll be presenting via Zoom screen sharing. When your time is to present is up, Luke, our master host on this Zoom chat room, will be assigning you as co-host, where you'll be able to share your screen and unmute yourself. Okay. So for those of you who are unfamiliar with Zoom, the share screen button and the unmute button or mute button are there. Okay, so just showing this to you now because a lot of people, not everyone is familiar with Zoom, and those who are unfamiliar will typically fumble a bit looking for these buttons. But I'm showing you now, these are the buttons that are important for screen sharing and unmuting later. Okay, another highlight for today's event would be the poster session. So right after the spotlights, we move into the poster sessions where you can interact more closely with the audience. Now, we had a technical issue with Gatherly. It worked perfectly yesterday in block A, but it's not so much a technical issue, but a scheduling issue. They didn't enable CVPR main organizers didn't enable Gatherly for block B. So we don't have Gatherly today. We came up with an alternative, which is to use Zoom breakout rooms. Okay, so if you're wondering what are Zoom breakout rooms, that's the button that you should focus on. If you click on that button, this list of rooms appear. So we have 9 breakout rooms, 1 for each paper. Okay, so paper authors who are presenting your poster today, go into the room number assigned to your paper, right? If your paper 5, you go to room 5. If your paper 7, go to room 7. And audience, you are free to join and leave any of these breakout rooms by yourself. You don't need us to assign you to any of the rooms, okay? We've set it up so that you can join and leave by yourself, okay? What else did I want to say about this? No, that's all. All right, so not everyone is familiar with Zoom. Not everyone is familiar with breakout rooms on Zoom. That's a button that you want to look for. Okay, so again, follow the paper number that's assigned to you to go to your breakout room for paper presenters. And with that, I'm done with my welcome message. Thank you very much for your interest in this workshop. Thank you very much for contributing to the workshop. Let's begin block B. With that, I hand over to my colleague, Clinton.
Yeah, thanks, TJ. Good morning, good afternoon, or good evening, everyone, depending where you're all dialing in from. So as TJ said, my name's Clinton Fuchs, and it's my great pleasure to introduce our first keynote speaker for this session, Dario Izzo. So Dario is the scientific coordinator of the advanced concept teams at ESA, the European Space Agency, where he coordinates both scientific activities of the Advanced Concepts team, as well as manages the interface with the rest of the European Space Agency. Dario graduated with aeronautical engineering from the University Sapienza of Rome in 1999. He later obtained a second master in satellite platforms at the University of Cranfield in the UK and a PhD in mathematical modeling in 2003, also at the University Sapienza of Rome. Dario himself is a major proponent of AI and a champion for the use of deep neural nets to solve problems in space. He led studies in interplanetary trajectory design using AI and was also responsible for starting the global trajectory optimization competitions, the European Space Agency's Summer of Code in Space, and the Kelvin's competition platform, which brings together AI and space researchers. So you'll join me virtually in welcoming Dario for his talk, and I'll now hand over to Dario.
Thank you very much, Clinton. So I'm going to share my screen, I guess, at this point, and hopefully I can share the correct window. And you should be seeing it now, except it's, yeah, you should be seeing it full screen as well. Are you? No, you're not. Great. We did this before. Okay, let me see what's going on. Okay. I have the window from your screen sharing. Okay, I'm going to stop sharing and share again. Let's see if this works. Share screen again. I'm going to share the Google slide without this screen, as I did before. And start sharing. Here it says that I'm screen sharing. Do you see anything?
Screen sharing, yes.
I remember earlier you pressed the present button at the at the top, and
yes, I did this as well, but let me do it again. I guess like this, presenter view. Are you seeing anything?
Yeah, we can see it. It's just quite small. It takes up about
Yes.
half the size.
Yeah.
Oh, there we go.
Okay, great. So thank you very much, and I'm gonna then get to it. I will talk to you about this deep space learning, which again is the sentence that we use to indicate the use of the latest deep learning techniques and into interplanetary space missions and interplanetary exploration. This is work that was done mainly in our team in the last, say, 10 years, and I'm going to summarize. So there's a lot of people involved, a lot of my colleagues that have helped, and are really, this is more a collective presentation than a personal one. From the Advanced Concepts team, where I work, we did in fact a lot of this work. And today I'm going to present 4 or 5 ideas. I think that I hope you'll find new and interesting. But first, let me start with some mood slides. So this is pictures of objects, irregularly shaped objects that we have been visiting in the last 15 years with our spacecraft. 20 years actually. Eros was the first one, the first high definition image we got of an asteroid belt asteroid. Itokawa, visited by the Hayabusa Japanese spacecraft, is another one that showed us how asteroids can be boulder piles, aggregates of loosely aggregates of boulders. This is, of course, our favorite one, since I'm from the European Space Agency. This is the comets that we've been recently landing on. Rosetta, where we can see from these images an incredible definition of the details of the objects and the irregularity of this shape. And this is Ben that we heard about, I think, yesterday, from the OSIRIS-REx mission, also very high definition pictures. And what I want to show you basically is the amount of complexity that goes into and decisions that go on board into a mission that goes there. So from launch, this is the mission profile of a mission which is coming, 2024, Hera from the European Space Agency, really nice missions, but that's not the point of the presentation. So basically, from launch, we have a cruise phase where we have to go where we want to go, and that's we have to take the decisions on where to fire our engines and how to cope with noise uncertainties and the planet's moving. Once we arrive at the asteroid or at the body or at the exploration target, we need to study the environment. So there is a lot of commissioning phase. The antenna gets the communication to the ground, stations get established. We start gathering a lot of information from the onboard payloads and characterizing the whole environment. And hopefully at the end we have a model of the dynamics of the spacecraft and of the satellite. And the satellite gets a model of the asteroid and the gravitational environment. Maybe it can land, release some payloads, and start the scientific part of the mission, which typically for asteroids and irregular body is about characterizing the surface, the gravity, the inner structure of the asteroids, maybe landing, taking a sample, and go on. So all of this is currently done, and we are pretty successful in doing it. And it doesn't use much of the latest trends in automation, AI, and intelligence, because it relies on constant communication on the ground. There's a lot of work being done on the ground, and I hope in the next 20 minutes or so I can convince you that most of what it's done can be moved on board the spacecraft using deep neural networks. And I think that's what will happen in the next 20 to 30 years. We will see an increased use of this, and maybe the complete substitution of ground station communications to give a new and unprecedented level of autonomy to this type of exploration mission. And it's something also where you can help, and that's why I'm going to show you a few links that you might want to record. Here is where we put a lot of our data set that we create in collaboration with our international collaborators, and we make them available for the future. So and another interesting and related website is Kelvin's, where we host competitions again on data sets that we curate and completion that we curate, targeted to enhance and improve the use of data and machine learning and in general intelligence on board of spacecrafts. But the presentation today is about 4 main ideas that I want to pitch here, and 2 are relatively consolidated: GetNets and geodesy nets. These are deep networks that we have studied in the past, and we propose them as to substitute blocks on board of the spacecraft. And EclipseNet and Euromorphic spacecrafts are some running researchers that are less consolidated, but we think have a very bright futures. So I'm going to start with this with the GetNets, which is guidance and control networks. So what are these? Well, each object, be it a rover, a rocket, a quadcopter, or a satellite, has of course a state that he needs to know where it is at, and this is usually given by the navigation system. It means I'm here, I'm with this orientation, I have my flexible parts in this state, and of course after this, the spacecraft or the object needs to take a decision on what to do. This requires path planning, requires an objective, of course, to have, and all of this we think can be done through a deep network that transforms from the state directly through dense layers to the optimal control action through a number of tricks that we studied, and the nonlinearities in particular. What is important is that the nonlinearities used are infinitesimally differentiable. But the point is that this type of network needs training data, and that's the bit of the bottleneck. So how do we train a network to take the optimal decisions, the best decision possible for all these diverse systems in all diverse configuration in completely unknown, let's say, unknown exploration scenarios. So fortunately, to Soviet mathematician Lev Pontryagin, he solved one of these problems for us. He solved the problem of finding what's the optimal control for a deterministic system with this very celebrated maximum principle theorem, which he did at the end of his career after he gave much greater contributions in his mind, at least, to mathematics. But he solved this for us, and this is the basic of rocket science. Unfortunately, To apply this, we need to solve what is called a two-point boundary value problem, which means that we need to, starting from some state, we need to propagate forward in time a set of differential equations doing multiple shooting up to when we actually get to where we want to get. This two-point boundary value problem is difficult. It's numerically complicated, and therefore, to create one example, one optimal example, to then teach our network how to behave, requires time. And then we have to do it for another initial conditions, another initial conditions, and another initial conditions. And this is a lot of work, and it's difficult. But what we notice is that all these trajectories have a point in common, which is the target point. And the only difference in the target point, since the state is identical, is actually the gradient of the value function. So one of the ideas that we built, and it was very successful, is to backpropagate from that point, randomly instantiating the value function gradient. And like this, we transform the problem of generating one sample to get in our data set to just a numerical propagation of an initial value problem, initial value from here backwards. Of course, we lose the control over the initial condition, but that's fine because it's a data set and we want to learn from. We don't want to solve the problem from an initial condition. So this allowed us to create immense and huge data set. This is, for example, for an Earth-Venus transfer, gigabytes of data where we can learn from. And it's very, very nice for, of course, deep learning type of techniques, and in particular for GetNets that they can be trained on this. And now we can actually have a network on board, which is completely robust to noise and also to some extent to failures, because it can replan itself in real times. Of course, we can't prove this real-time angle from the point of view of a spacecraft. Here, by the way, you see the errors, which are very low on the prediction from the network of the thrust and the thrust direction. We're talking about 10 to the -4 here, and sub degree level here. But I was saying, so we cannot test it on board. So what we do, we test it on quadcopters. The principle is the same. This is a quadcopter type of trajectory in 3 dimensions. This is a 2-dimensional slide of it. Again, data set created with the backward propagation of optical samples. This is the network predictions in time. You see they match perfectly the optimal control, and you can put it on board in real time. This is a time optimal case. I'm going to show you very quickly the video on the left. This is the differential flatness technique, which is time optimal control, which is used in drone racing, which achieves this very simple maneuver in 2.3 seconds. And on the right, we have on-board real-time GetNet implemented, which does the same maneuver in a much shorter time, with no surprise, because that's time optimal. So this is a bit the first thing I wanted to show you. These GetNets are solving the problem of how to get there without limiting the communication to ground station, because everything can be actually put on board. But once we arrive there, there is this characterization phase in which we need to know the environment, the gravity, the dynamics of our spacecraft. And that's the second ideas that we had, which we call geodesy nets. So how do we characterize the gravity of a planet? Typically spherical harmonics. We have to do during the commissioning phase. We need to get all the coefficient of the expansion, and it can be complicated, but most of all, they don't converge. For irregular bodies especially, they don't converge at all inside the so-called Bridging spheres, which is indicated here. Then there are other models like polyhedral gravity, and we would have also the Mascon model type of effects, but they all have issues. And so we thought, okay, what's new in computer vision, and what is that it's good at representing 3-dimensional objects? And we learned just last year, this was work done in the team and presented to the team by our colleague Dava Darksen, who's actually, I think, following this keynote. And he just put to our attention this incredible work in which basically we learn how neural radiance field, which is basically a deep network, can represent very complex 3-dimensional scenes and 3-dimensional objects in general. So networks have no problem into representing really high frequency content in 2-dimensional and 3-dimensional scenes. Now, in the case of neural radiance field, the original intended use is the solution of an inverse problem, the inverse rendering problem. So given a number of rendered image, what is the object that would create those images? And this is done by ray tracing and inverting things. But this was very good news for us, and now I'm going to give you a few teasers. Because again, complex object can be represented, and you can well understand where this is going. But first of all, we can represent, for example, exactly using the same type of technique, the scenes from the Earth as taken from satellites. And this is the work that was presented actually yesterday from our colleague Dava. who was able actually also to include the shadow information in the network as to make the network render not only the scene from unprecedented views and unknown views, but also from unknown sun angles. Another interesting work which is related to this, and that will be actually presented later by my colleague Anne, is about using and comparing NERF and graph. NERF is the neural resonance field, whereas graph is the generative counterpart to it, in order to represent and build on board again a three-dimensional satellite shape. And you can see here the precision and the richness with which the network is able to build this model. But most importantly, when we talk about irregular bodies, now we go back to asteroids. So that's what we thought. Well, maybe we can actually represent the three-dimensional structure of an asteroid. So we completely rewrote the same principle, and we call it neural density field. So now the network represents the density, the mass density of a three-dimensional object, the asteroid in this case, from Cartesian position to the asteroid density. And then from that, we can actually work out from the network output the potential, gravity potential that would be generated by such a density distribution, and the gravity accelerations, which we can mesh to measured ones, because the spacecraft during commissioning is orbiting, and we can back propagate as to learn the coefficient. And with respect to previous approaches, we retain the same precision, incredibly, but we have a differentiable model which works everywhere, which also accounts for heterogeneous density, does not need any information on the shape, can utilize the shape if it's known, and is very accurate in the near field. So these are some ground truth we tested this technique on. These are Mascon models to establish the ground truth, but I wanted to show you here the results of the training pipeline. So here we start with a random network which assigns a random density everywhere in space, and then slowly as the training progresses and it gets exposed to new orbital data from the spacecraft, you see that the network understands the exact shape. This is actually the 65P comet. The exact shape of the comet, and places the mass exactly there. In this case, the model is uniform. He actually also understands that the mass density inside the comet is uniform. Now we don't know what the mass density inside the comet is, and this is using synthetic data. So when I say it's uniform, it's because we used a uniform ground truth, which was a synthetic ground truth. And here we see in Ben instead a nice movie representing this neural density field in 3 dimensions, in which you see also the inhomogeneities inside the asteroids, as Ben is known to be inhomogeneous. You see that in the equatorial bulge we have a much lower density area. So the network is also able to understand the internal structure of the asteroid and perform geodesy, and so augment the mission scientific return considerably. So we're really excited about this technique, which actually is relatively consolidated in terms that, according to our data, works very well. We need to cross-match and apply it to real flight data. But it's also related to a second idea we had, which is eclipse nets, which would come into play when you have to characterize your dynamics around the body or around the new environment. You need to know if you're in eclipse, if your spacecraft is in eclipse or not. In order to propagate fast your dynamic in such an environment, to activate or not activate the solar radiation pressure, you need to know whether you are in the eclipse cone of an asteroid or not. And this is complex. It's difficult, and if you want to do this efficiently, you need a differentiable way to represent such a border between the cone shadow and the Cartesian position. So we introduced what we call an eclipse function, which is for each point of view, for a random, let's say, viewpoints around an asteroid. In this case, it's Eros. You get a function that we can define mathematically as being positive if you are not in the shadow, and negative if you are in the shadow. That's the only important thing, because what we want is that it's 0 exactly on its border. And our proposal is basically to define it like this. We have we shoot a ray. If the ray doesn't hit the asteroid, you're not in the shadow, and the function value would be the distance from the ray to the closest point of the surface. Otherwise, if you are in the shadow cone, then you shoot a ray, and the tip function would be the amount, the length of the ray which is immersed inside the asteroid. And this is an example of the plot of an eclipse function in the case of Eros. So this is the eclipse net. Then we feed the network the direction of the ray, okay, with some, of course, tricks in order to have it more learnable, and the spacecraft position. And then we go through again some dense layers, in this case represented by the siren structure. Siren is basically trigonometric nonlinearities inside the network, which have been shown in the last years to be able to model really high frequency content with less problematics. And then in this case, we had to also add some skip connections to solve a gradient problem that was encountered for, we think, a numerical cancellation during training, for which we had huge spikes during the training procedure. With the skip connection, this is alleviated, and we get a nice and smoother decline of the fitness function. Does this work? You can judge here. This is the in red is the neural network 0 of the eclipse function as compared to the projection of the body. So the network learns exactly and perfectly, or at least very satisfactorily for the purpose, this eclipse function, and we can now use it in numerical propagator on board in order to propagate, for example, the pebbles dynamic or even the spacecraft dynamics with or without eclipse, because everything is differentiable and everything can be put into, for example, method based on with automatic differentiation on a fast numerical propagation like the Taylor method. So, and the last thing I wanted to show you is this neuromorphic spacecraft thing. This is really ongoing work, but it started from a bit of time ago, where we were interested to see what an optimal landing, in this case in the moon, is looking like. You see the differential equation of motion on the left and the Pontryagin solution on the right, with the rendered images of a synthetic on a lunar landing. So this is what a camera sees on board of a spacecraft when landing on the moon optimally in terms of mass. So this is important to remember that all these trajectories, all these dynamics need to be very, very precisely consuming the least possible fuel as for the mission to be safer and to cost less at the end of the day. So this is the mass optimal landing on the moon as seen from a camera, but we started asking ourselves time ago, what would an insect see during a landing like this? And we did this because we were interested in some neuromorphic sensors inspired by the insect eye, and the most basic of them are called the elementary motion detectors, which are basically sensors that are detecting contrast lines as they pass by. And that's because what insects do, they do not use absolute information. They use basically this optic flow information that is from their eyes, directly gathered from these photoreceptors type of things. And there was at the time, this was 2011, I think, there was a number of groups that were developing these sensors and also for space applications, and we tried to model them and develop them also for our purposes. And what happened here is that we put some synthetic simulations, and we were here measuring the optic flow during the rotation, the orbiting of a spacecraft around an asteroid. And you can see here the asteroid surface repeating itself in terms of the shape. This is the elevation of the asteroid, and as you spiral down in of course, the shape is repeated, but because you're getting closer, but the optic flow is augmented because, of course, you're getting closer. So this was very interesting, and it was a preliminary work, but then since then, a lot happened in neuromorphic computing. As you well know, now hardware is being produced by the big names, which are kind of inspired by this type of reasoning, and we have also motion sensors like the event-based cameras that are actually transforming camera images like this into event-based images. And here I'm just showing you an example. This is actually our own simulator of an event-based camera, which is for space, adapted for space conditions. We're still working on this actually with Adelaide University in order to match simulations to reality and have a better way of looking into this. But this is what likely, in this case, not an insect, but a neuromorphic sensor could look like during a landing. And now the problem, of course, that we're working on and we're trying to understand if possible, is to see if from this event-based data we can tie them up to, in our case, we think that neural networks spiking of the spiking type, in order to extract that information which is important for landing, which is certainly optic flow, but also, and it is a bit more difficult, of course, because it's fundamentally condition problem, the altitude of the spacecraft during the landing. And I think this is the fourth thing that I wanted to show you. This ends my keynote, so we have a bit of time for questions here and discussion. These are some references of the divided into the different things that I showed you today. So the guidance and control networks, the JODIS and the neuromorphic spacecraft type of things. On the neuromorphic spacecraft, we have a presentation exactly in this workshop on some early prototypes of our work. And with that, yes, I would maybe end the keynote and start to have some questions and discussion.
Thank you so much, Dario. That's fascinating work. So we now have about 5 minutes or so of question time. So if anyone's got a burning question, please raise your hand. In the reactions bottom at the bottom, you can raise your hand. Or if you like, you can put a question in the chat window. And then we'll go through them one by one.
There is a question on the chat by Andrew Clinton.
Okay, thanks, TJ. So Andrew's asked, as demonstrated by Courtney yesterday, deterministic systems are highly valued for these expensive deep space missions. Could you speak about how we might demonstrate the reliability of these neural networks for highly expensive space missions?
Absolutely. This is actually part of the. There's a paper here exactly on this topic. I didn't present it because, of course, I didn't have time. But this is very important work that we managed to do exactly for the GECNets. So for neural networks, now they are on board and they need to tell us what is the decision, of the optimal decision of our spacecraft. And people will say yes, but what if they go wild? What if it's wrong? How do you validate this? How do you make sure that this is the real optimal action? It's not going to end up in a catastrophic failure. Well, we can. So it's a false problem to think that neural networks today are not verifiable. They largely are, because they are differentiable objects. At the end of the day, it's a mathematical function. And if you do it, as I said in the beginning of the presentation, with nonlinearities which are infinitely continuously differentiable, then you can, using techniques, in our particular case, in this paper, we're using differential algebraic techniques, we can expand it into Taylor polynomials of any order and repeat the same type of studies you would do with normal H infinity control rather than linear control, rather than nonlinear control based on other principles. You can repeat that type of things and prove the stability. You can actually prove the global stability, or at least the local stability, but in a non-vanishing surrounding of your initial conditions and of your perturbances along the trajectory, and still prove that your network is going to lead you exactly to your final point. So that's the first thing. So the network is no longer a black box. It's actually something we can look in and we can know what it does using very similar technique to the one of control theory. Then there is, of course, software validation. That's also, I also think, is a non-issue. There are people working on the agency on how to verify and qualify the neural network, like how can it be sure that the output of the network is what I expect given the inputs. But that also is not things I'm involved in, but it doesn't appear to me as a showstopper. It's just there is work to be done because these are new objects and new things that we need to put inside very complex objects, as you said, and we cannot risk that they fail. But I'm very confident there is a lot of questions there, but there are no issues. So it's possible to tackle these things. And we showed this in one of our papers. There are also other people that are going and concluding very similarly.
Excellent. Thank you, Dario. Any other questions in the couple of minutes we have left before we move on? Yes, we got another one from Marius.
Hi, Dario. A great presentation. I just want to ask, does the agency plan to do any in-orbit demonstrations using neural nets for navigation in space?
So for navigation, that's an interesting point. Yes, we are starting to discuss the next generation technology demonstrators with neural network capabilities on board. Again, we're talking about inference, not about training. In the advanced concepts team, we are doing work actually on onboard training. But at the agency level, there is talk about the technology demonstration for onboard guidance and navigation based on networks. Yes, there is not yet a concrete mission that is being past phase B that is being developed with this onboard. But I see it coming. I have no doubt, and within 3 or 4 years we will have a solid plan on demonstrating this this network capabilities also for guidance, navigation, and control.
Excellent. Thank you very much, Dario. So I think at that point we're bang on time, so we might wrap up the Q&A section now. So please everyone join me virtually once again in thanking Dario for his talk. And I'll now hand over to Marcus to introduce our next keynote.
Yeah, hello, this is working, very good. Good day or evening to everyone. Welcome to our last keynote speech for this workshop. I'm Marcus Mertens from the European Space Agency, and I have the pleasure to introduce Professor Yang Gao from the Surrey Space Center to you now. Professor Gao works there as the head of the STAR Lab, which specializes in visual sensing and navigation for extreme environments. She started her career at the Nanyang Technological University, where she obtained the BNG and her PhD before she was awarded a postdoctoral fellowship from the prestigious Singapore Millennium Foundation, working on autonomous and intelligent vehicles. After joining Surrey, she was involved in numerous workshops and conferences, edited and co-authored 2 textbooks and over 160 scientific papers. She is editor-in-chief of the Journal of Field Robotics, as well as associate or guest editor on international journals like Frontier Robotics and AI, IEEE, CIM, CIS, AESM, and others. Professor Gao can look back on over 20 years of research experience in developing robotics and autonomous systems for space or other extreme environments, contributing to projects from UK Research Innovation, the Royal Academy of Engineering, the European Commission, the European Space Agency, the UK Space Agency, and several industries like BT, Airbus, OHB, Neptec, or Sellafield. Furthermore, Professor Gao has been actively involved in the development of real-world space missions, including ESA's ExoMars, Proba3, Moonraker, and others. We're happy that she agreed to join us today, and I'm excited to hear what she has prepared for us. Professor Gao, please, the floor is yours.
Thank you so much for the very kind introduction. Can colleagues see the shared screen? Is that seeable from everyone? Excellent. Thanks again for the organizers' effort to put the workshop together. It's a great honor to be here and talk you through some of our work on robotic vision and machine learning that's supporting ongoing and future space missions. I would also take this opportunity to share some of my personal views on the long-term vision in AI robotics to achieve sustainable space exploration and exploitation. If we could take the first few seconds to look at the history of robotics in space mission, it's not surprising, I think, to everyone to say that AI-enabled robotics has been helping to diversify the mobility and increase onboard autonomy for space robots. This figure helps to illustrate, if you like, for some of the key milestones in space robotics or robotic missions since 1960s, and you can see quite clearly the change or evolution in the demand of the level of autonomy on board these robots in our missions. And in the early times, when we have very active Lunar and Mars missions between the Soviet Union and the United States, it is very clear robotic forms vary from assembling tools to surface rovers, and they're primarily looking at operating through remote control and some of the pre-embedded or pre-programmed commands, or what we refer as automatic operation. And moving on, most of the robotic arm operations on a day-to-day basis in the International Space Station still remain largely teleoperated. Of course, there are some ad hoc situations that they do have some autonomous functions. And closer to 2020 or into the 2021, we've seen a large range of extraterrestrial exploration using rovers, using different robotic platforms. And this has been carried out by multiple nations to the moon, Mars, asteroids, comets, things you hear so far by various keynote speakers. And they certainly try to stretch the onboard autonomy for robots, more into the semi-autonomous operation, at least by default. Looking ahead, I think we as a community in the space is really keen to develop more robotic explorers that has full autonomous operation and can deliver range of mobility and locomotion capabilities. There will be more vision, I think, looking into co-working between human astronauts and robots, whereby the robots would be expected to be either fully autonomous or have a shared autonomy with the human co-worker. If I could split, this vision into two principal space scenarios, I will start with the orbiter first. The landscape for the orbital scenario seem to suggest in the time frame of 2025 to 2035, there are many on-orbit applications that require more advanced AI robotics capabilities. Some of the missions would look at clean space, such as debris removal, orbit assembly, deployment, satellite servicing, constellation formation flying, reconfigurable spacecraft for lifetime expansion or adaptability, and also reducing the satellite costs. And we're also looking at, quite into the different challenges come from, for example, whether you're working from pseudo-fixed platform, for instance, ISS, or free-flying satellite, which impose different technical challenges to AI or robotic vision. Similarly, the target you are tackling with your robotic system also varies between, for instance, cooperative target to non-corporate targets. Again, that implies different challenges and requirements with robotic vision or machine learning. Next, I'm going to give three project examples which has been carried out in my research lab. Just give you a taste or flavor of things we can do using robotic vision and machine learning. The first example is in visual sensing for formation flying spacecraft. And here we're working with our industrial partners towards the European Space Agency's Progress 3 mission, where this is an orbital demonstration for precision formation flying between two spacecraft to study the solar corona. And the technical challenge for the visual sensing is to try to achieve high precision attitude determination and measurement between the two formation flying spacecraft. And here we use a laser-based fine lateral and longitudinal system for relative attitude determination between the two spacecraft to achieve a high accuracy of 300 micron at the furthest distance of 250 meters between the two spacecraft. So for the longitudinal system, is a measurement of the laser signal phases that we're relying on. The lateral system measurement is the most challenging, and we have to use, for example, some of the machine learning techniques for the calibration, both offline and on board, to track the beam movement because of the fine accuracies that the mission requires. Due to time limitation, I cannot go through the technical details, but there are reference papers here you can easily pick up and read. The next example is to do with visual-based orbital navigation. I will let the video play while I'm talking, but here the key challenge we are trying to address is autonomous and low computational relative navigation of spacecraft for orbital servicing or assembly work. So here I stress the word low computation because even the modern spacecraft are still largely limited by some of the hardware constraints, such as onboard processor. So here we adopted monocular vision-based post-estimation algorithms to help fulfill that desire of low computation and fast speed that is workable in real time. And we use a convolutional neural network-based deep learning to help achieve high accuracy adaptability in real time, just to care for things that we were not able to pre-model, even though here we're primarily talking about corporate target because it's through servicing and assembly. So this has been validated both by photorealistic orbital visual simulator, which is developed in-house. We're making that license available to both academic and industry. It's also tested through orbital robotics hardware testbed. At the moment, we have a TRL of 4 to 5. So here I'm showing you on the left-hand side some of the pictures taken from the ORIS, our real or photorealistic simulator to do the initial concept validation. And on the left-hand side, I'm playing you a video that's showing the real-time demonstration using our testbed, where we're trying to simulate particularly the lighting conditions in space so that we can test exhaustively and making sure that the algorithm works reliably and robustly. Again, you have more videos from our YouTube channel and technical papers you can grasp to know the technical details. So this is one of the rounds that's showing that after the establishment of the relative pose between the target and the service arm, the docking is actually achieved successfully. The third example for the orbital scenario I'm showing here is to do with, again, visual-based orbital manipulation, in this case, and grasping. Here, the objective is to really service future active debris removal missions. In fact, there are a lot of talks about it right now by space agencies across the world. So the aim here is to, again, achieve autonomous robotic manipulation grasping, but in this case, the target become non-cooperative. So we have to be very careful with the challenges there that is pushed back to the vision system. But again, here, there is a desire of having low computation, fast speed, real-time solutions. Here we use very sparse point cloud sensing and video-guided GNC. So to acquire the sparse point clouds, we simulated the system in our hardware testbed through a degraded real sense sensor, which is very cheap to achieve even in some of the foreseeable future space missions. And it has to work with noise and uncertainty environment, so the algorithm is resilient in that sense. It's demonstrated again, as you can see, by the played video right now on the slide, where we tested it both using our digital simulator and the physical simulator, which are the twin system to each other. Going to the stability or robustness of the algorithm, which was a question to the previous speaker. Here we also look into that in terms of verification, validation. Similarly, we adopt a two-stage approach. We'll perform the V&V on the algorithm itself offline, and also simulate that in real time. There is also a real-time control feedback system to ensure the robustness and convergence of the control of the manipulator. So move to another, one of the other principal space scenario, which is the planetary surface. As people know, this is again another very popular environment that a lot of relevance to robotic applications. If you look at the landscape or looking over the horizon of this scenario, we can probably looking at two stages right now. which is beyond 2020. We are looking at a range of ongoing plans of sample return missions, such as the Chinese Chang'e 6, lunar sample return, or the ESA and NASA collaboration on the Mars sample return. And these are typical mission scenarios that involve sample fetch rover that need to explore unstructured terrain and collecting some surface or subsurface samples using robotic means. Or you're looking at beyond 2030s, where the goals there is to look at manufacturing, assembly, in-situ resource utilization on planetary surfaces, or even small body surfaces. So this, for instance, there's ESA's Moon Village, there's a Chinese-Russian Combined International Lunar Research Station. There are a range of initiatives that to do with commercial lunar exploitation exercise. And here, what we are likely to have is heterogeneous robotic elements, building infrastructures on those extraterrestrial surfaces, and human robot ecosystem around the south pole of the moon. Similarly, here I'm giving 3 research project or mission development examples where robotic vision and machine learning can play a great role. So first example, if a project that we worked in collaboration with Airbus, here is really help to facilitate sample return or ISRU missions over the landscape. The technical objectives or challenges is to achieve autonomous visual Gen C for high accuracy robotic arm placement for planetary surface sample acquisition. So again, I'm playing a film while I'm talking to help you, visually grasp the concept of the design here. So the research here proposed a visual saliency-based approach to address robust feature tracking on homogeneous scenes, which is common on planetary surfaces such as Mars, where, for instance, you have very rocky terrains that is very, very challenging for computer vision to tackle, and particularly when you are very close into the rock, well, you lost the boundaries of the rock surfaces, and that's where the algorithm can get really confused. So here the technique, again, adopt AI algorithms to use and perform a very good trade-off between the computation load and the detection accuracy and precision. Again, I'm stressing the importance of acknowledging that the space hardware, due to the radiation constraints, remain very limited on its onboard processing capability. So as designers, as solution providers in machine vision and machine learning, we have to be very honest about these limitations, hence reflect that limitation in our design. So again, there are quite detailed technical illustration of how the techniques actually perform the trade-off in real time and satisfactorily address the accuracy and precision is detailed in the papers given here. The second example in this category is work we did with big data processing for lunar surface soil property characterization analysis. Here we are collaborating with Chinese Academy of Sciences using that data come from Chang'e 3, U2 rover, the panoramic data that returned very rich, very high resolution surface imagery of the landing site of the rover. However, unfortunately, they don't have dedicated tool to understand the soil property because that's just the design of the mission at the point of time. Therefore, we have come up with a solution that allows them to perform a very deep analysis through, for example, shade-from shading combined with our knowledge of terra mechanics models, and applying the machine learning to estimate the soil property. And the further beauty of that is we allowed the technique to compare with the data come from the Apollo landing site and the lunar landing site from the previous US and Russian missions, and draw a very important conclusion as to how the soil property compares, and how they distributed on the surface of the moon in equatorial region. The third example I'm giving today is in the planetary surface scenario, is our work in relation to visual data processing for surface navigation operation in support of ESA's ExoMars mission. So this is directly relevant to the 2022 rover mission, which of course has been delayed from this year to next year due to some of the COVID issues. And this is the work that connect to the panoramic camera payload, which is principally a scientific payload on board ExoMars 2022 rover, and with emphasis to characterize the biological environment on Mars. Well, what we did as a contribution to the payload team is to extend the processing of the image data to allow us to reconstruct the Martian surface and to facilitate the rover navigation operation planning. So here, the development is of course a team effort, which we contribute to in collaboration with UCL and also the GR from Austria. And here we propose a software solution called Mission Specific Data Processor, combining the data coming from PanCan through a visual data fusion and learning-enabled object detection, self-learning agent to allow a GIS system to be developed and created with both geometric information, scientific information, as well as information that enables safe operation of the rover from the engineering team. So with those very speedy tour I gave to the audience today, I hope that gave colleagues some idea about the envisaged perspectives of the role that AI robotics is playing in ongoing and future missions. But I still want to look a bit further ahead as probably a scientist, is to look at the AI robotics enabling more sustainable in-space operations. I highlight the keyword sustainability here. In the near midterm, I believe the key challenges imposed by the space environment and spacecraft design constraints requires roboticists to look into the following: low computation, high accuracy, 3D mapping, and perception. I think we tackled quite a large portion of those already, but they're still allowed to be done. Energy optimized locomotion system in terms of mechanism and control. A lot of things machine learning can contribute. Resource aware computation and data processing for parameter tuning. This is very important because there are a lot of criticism towards machine learning because there are a lot of parameter tuning involved, and sometimes that make people inconfident in terms of reliability of the algorithm we are producing. So there has to be a lot of research effort in that area. Hardware software reconfigurability, self-verification in runtime. Again, this is important, and there has been questions already from the audience about that. In the long term, what we really need to achieve is long-lived, robust mobility, autonomy for next generation spacecraft. Something can work 24/7 in space, like a space factory, rather than we have to have human interference all the time. So here I would like to call for a community effort. And this is just one of the examples to move from the weak AI to strong AI. So the AI, the embodiment of artificial intelligence, robotic vision, processing, cannot be an afterthought. It has to be embedded at the very start when we design spacecraft, when we design spacecraft subsystems. And this is just one of the examples we did with a more generic, reliable, reusable software architecture that we can use for very complex space systems, such as involving multi-satellite heterogeneous robotic forms. And they are also embodiment of reliable machine learning planning software agent. For instance, you can use ontology-based modeling to partially achieve that. So with that, I would like to conclude my talk and thank you all very much for listening to my talk.
Well, thank you very much. This is was very enlightening and completely on time. We are very good in our schedule. So we have probably time for 2 or 3 questions maybe. If you want, you can type in the chat or you can raise your hand. Yes, TJ has a question.
Thank you, Marcus. Great talk, Yang. I'll jump straight to a specific question first. In one of your slides, you showed work using photorealistic rendering of spacecraft in orbit to achieve machine vision, I suspect, for the training phase. This is kind of aligned with the work showed by Dario earlier, where simulated data was used for spacecraft GNC. But what's different in the vision case, though, is that there is this domain gap issue, right? The simulated vision, as photorealistic as we want it to be, it's not the same as the real thing. What's your comment on that?
Yes, I think as a roboticist, and particularly working on real-world missions, I think that's an ongoing problem. On one hand, we see a lot of space industrial primes such as Airbus. They've been developing some of the ad hoc simulators in-house, and which they can use for specific mission development. But there's nothing very generic enough that allow collaborative work between academia and industry, things that can co-use by both. There's indeed a shortage of that. That's why we have come out with Orvis, which really aim to be a benchmarking tool. Of course, it can be used as preliminary validation. Facilities, but I was personally more pushing it or promoting it as a benchmarking tool, so to really allow the community to agree or build some consensus around some of this benchmarking data sets. And of course, ours could be just one of the many. And so that community, just like other application domains, which we see in automotive, for instance, or other industrial application domains where they have the data sets that are widely acknowledged and accepted by the community. They can use it, for example, in key ground challenges, so everybody can apply their algorithm against the same set of benchmarking tools, so that we can also benchmark and realistically compare different algorithms. So that's very, very important from the development phase. But also personally felt through my own involvement in real-world missions that this kind of tools also need to be used maybe during the mission operation as well, because it's very important. We see a lot of these interplanetary missions being extremely challenging. Failures almost is foreseeable. maybe it's not a complete mission failure, but the subsystem faults could happen from time to time. So I think this kind of tools are extremely important for engineers, operational teams to actually use during the mission operation to help recover as much as possible. So that's my view, and I do call for collaboration in developing this kind of tools or acknowledging, verifying these tools by the community as a collective effort.
Okay, if it's a very quick one, we have still time for another question, if someone wants. Maybe I can follow up on this reality gap. So usually, if you train the neural networks, there's some sort of simplification ongoing. Like if you train a network for optimal trajectories, some of the optimal trajectories are not possible in reality because, like, the robotic arm may not be able to actuate sharp movements or such constraints. So in practice, how do you deal with that? Would you say this needs to be incorporated into the training already, or is this something that you would solve with additional systems or redundancy?
That's interesting because from research point of view and mission development point of view, I think the answers would be quite different. Because with space mission development, very often we'll go through a quite rigorous and systematic development process. So those points will largely be addressed during the design. So it's either achievable or not achievable. But from the research point of view, if we want to push the boundaries of the technology, my view or our research practice is that we need to come up with either software solution or hardware solution. So meaning from the software point of view, I think we need to look at very intelligent ways to, for example, work on the inverse kinematics to make sure there is no singularity issues when you want to control the manipulator to a place that you, for instance, is challenging. Well, from the hardware point of view, there are also ways you can, for example, at the moment we are looking at some of the soft deployment of some of the manipulators, and we, there's some soft joints that we can look at to help improve the what we call degree of freedom or redundancy degree of freedom into the manipulator, so that we can avoid that system, in the hardware way. So I think it's both software and hardware has to work in conjunction with each other.
Okay, thank you very much. So that concludes our keynote session. And next on the agenda, we will be coming to the presentations. And I will hand over to Luke at this point.
Thank you, Marcus. And thank you very much to Yang and Dario so far for amazing presentations. Coming up now, we have 9 of the spotlight presentations, 4 presenters that have already had a chance. I'll be giving you co-host permissions at the start of the speech prior to yours, so you can have a look at the controls you'll have to enable you to present. Please do not present until it is your turn. You've been let know it's your turn to go. Andrew, should we have access? I'll be keeping a 5-minute timer going, and I'll try and raise my hand at the point that we are starting. And so at the point where you have 30 seconds left, but it's best to keep on track of the time yourself as well. Andrew, when you're ready, feel free to take it away. Having that same audio issue as earlier.
Is that resolved?
Better. Excellent.
Thank you. Okay. Right. So my name is Andrew Price, and I'm from Tohoku University in Japan. And honestly, it's been quite a delight participating in this workshop. So thank you for organizing, and thank you for giving me the opportunity. So our research is primarily interested in the orbital debris problem. I think most metrics that we look at are showing that this is going to be an increasing problem moving forward. We have more mass, we have more objects, and I think we're going to have some challenges in the future. And of course, one of the primary challenges in interacting with orbital debris is the large number of unknowns, where this debris comes from, and additionally, various properties about the debris. And we need to obtain this information remotely, especially for non-cooperative debris. And so this sort of forms the core, in my opinion, of a competency we need to develop that will be extremely useful for in-orbit construction, for asteroid mining, and for, of course, orbital debris removal. So in my lab's first steps to get involved in this sort of work, we looked at this Hayabusa 2 space probe case study. So the Hayabusa 2 space probe is a Japanese space probe that visited the Ryugu asteroid, and when in its vicinity, it deployed a number of rovers. One of those rovers was the Minerva 22 rover, as depicted in the center of this slide. And you can see it's a really symmetric rover. Additionally, and unfortunately, the rover experienced a fault during its deployment, so it couldn't share attitude information. So essentially, we have a non-cooperative case study. Now, the Japanese Space Agency estimated where the rover landed on Ryugu by doing some orbital analysis by using images captured by their telescopic camera. We performed a similar deployment analysis using images captured by the wide-angle camera during deployment. So those are the images you see on the right. And you can see there's some various noise artifacts. You can also see that the target goes away from the camera quite quickly, and the amount of information contained in those images is, put lightly, very sparse. So our first approach is relatively simple, is projected geometry. We know the size of the target, so we can estimate how far it is away. Unfortunately, if you don't know the attitude of the target, you don't necessarily know at what angle a plane or an edge comes to intersect with the image plane. So you can't be perfectly accurate. We help mitigate these errors by modeling the target as a sphere. And you can see some of the results at the bottom of the screen where we estimate the center of mass, and we perform a least squares regression on the velocity term to converge to an estimate there. And that worked well. But for estimating the tumble, or the estimating the various attitude of the target as it, of course, is from these images, needs something a lot more involved, which is a machine vision approach. And of course, to train a machine vision system, we need a data set. And of course, our application is unique, just like everybody else's is. So we had to create a data set from scratch. And so we started with SolidWorks renderings. Now, this is interesting because I would argue that these renderings are relatively low fidelity compared to what we're seeing in this workshop and in other cases. We had very good geometry information. We had very good solar panel information, but we didn't have detailed information on the wiring or maybe the surface or reflective surface properties of the satellite. Instead, we focused most of our attention on reproducing the image artifacts to help bridge that domain gap. So we worked on bloom, motion blurring, and contrast adjustment. This was a very reiterative process, and we looked at a lot of different metrics, and especially the image histograms. You can see as we went from SolidWorks to the modified, I think we did a relatively decent job of replicating the real images. So here we have the pose estimation pipeline. We adopted a convolutional neural network to estimate landmarks from the images. So we get a number of landmarks. And then we use a P3P algorithm to estimate the pose. But since it's a symmetric object, we don't get the pose. We get one of the few poses that are possible. And so as an octagonal prism, we actually have 16 possible poses. And so we could always estimate the axis of symmetry, but which of the 16 possible poses, that's a bit more of a difficult question. And I believe we'd need even more images to sort of propagate the tumbling through the images to isolate a single solution. But at the bottom of the screen, you can see tumbling of renderings that I created, simulation, and I deleted certain solar panels to create an unsymmetric target. And in this case, it becomes relatively much more straightforward to get the single pose. Okay, so to wrap up, we did validate the JAXA velocity deployment. I think we got relatively accurate compared to them using a completely independent set of images, which is exciting. And we did this using a relatively low fidelity render baseline, which I think is exciting for the other people working on their own projects, because we all need to have our own data and it has to come from somewhere. And perhaps high fidelity isn't necessarily always the most important part when we need to extract information or train these data sets, these systems to work on these images. In our case, the image artifacts was the most important thing. But we worked with some very challenging images, and we still got the axis of symmetry for most of them. And it was very exciting. So With that, thank you very much for your attention.
Thank you very much, Andrew. Next up, we have paper 2 by Dung An Huang. Dung, do you have access to share your screen now?
Just wait for me a bit. Can you see my screen?
Yeah, you're good to go.
Okay, then. Hi everyone, my name is Dong. I'm a master student at the University of Adelaide, and this project I have in some of my last undergraduate year with both Chen and Professor TJ. Well, first introduction, in recent years, there has been less investment in space technology with most of the state-of-the-art using deep learning. This method often requires a lot of well-annotated training data to have decent performance. Unfortunately, there's currently no public available spectrograph dataset for computer vision types. So far, SpeedRun and URSO tools are the closest and the legit dataset related to this topic. However, they focus on both estimation and don't provide simulation or detection annotations. Well, that's why our contribution is this project is to create the first dataset for spectrograph image simulation and object detection types. The dataset will include both simulate and real spectrograph image collected from different sources. With each object being segmented into at most 3 bands, solar panels, antenna, and bodies. We also set a benchmark of simulation and detection for spectrograph using the current state-of-the-art models. Well, the reason there's no available spectrograph dataset is due to some challenge in collection and annotation. The first one is because of the scarcity of available spectrograph image. As they are sensitive data, satellite image are often not made public with high resolution or can cost a lot. The second reason is that spectrograph often have unorthodox shape and delicate but which makes them mass expensive and time consuming to label. Below, you can see a true example of this challenge. In the first image, the background is too dark to be able to discern the spectrograph clearly even with human eyes. While on the second one, it just make it quite expensive to manually annotate the mark correctly. Well, now I will briefly talk about our methodologies. During the project, we consistently follow 6-step bootstrap method to annotate and collect datasets. Firstly, we gather a small number of spectrograph images in order to test current state-of-the-art method for segmentation. The fundamental we use to annotate the mask is a segmentation tool from the University of Toronto lab. It's in this link here. Actually, there's currently a better annotation tool in this suite, but it's still in the beta state and a bit difficult to create a large number of maps. And the reason we choose this tool is because it allows us to break down the object into complex parts and manually annotate them as polygon. Also, we finish select tool, we get a large number of satellite images from different sources. A hard part of this step is to remove duplicate images as they come from different sources. So in order to do that, we use agglomerative clustering and a search engine using chi-square distance to remove duplicate ones. All images are pre-processed by removing unnecessary parts such as random words or symbols. Once we finish annotate the mask, there's another post-processing step. Since the mask quality generally improves as with the project progress, we use bootstrap step to go back and improve these maps of the data sets. However, after around 1,000 masks, we use another way to annotate the mask. Using the first 1,000 image as training set, we train 3 simple model to predict pseudo mask for each part of the spectrograph and then remove flaw one and overlaps the high qualified one to create a pseudo full mask. After that, we just need to annotate the missing part. However, this method result in a bit loose maps, and in some cases, the part map do not completely overlap each other. So you can see in the post processing step, we have to remove the unoverlapped part of the main body here. Yeah, you can see some example of the annotation from our data sets. Next, we have some simple statistic information about the data set. The data set includes in total 3,117 images with uniform resolution. It includes map of over 10,000 baht of 3,667 spacecraft. There are around 1,005 mark and 2,100 Charlie coast mark divided into two set train and test. Its spectrograph can be as small as a few hundred pixels in size to nearly a whole image. And below is a few graph represents some statistical information of the data sets. Once we get the map, we set out the benchmark for the data set. We have base benchmark for object segmentation, including or economic background class segmentation for each individual bus and object description for the whole spectrum. For segmentation benchmark, we use set of the art models such as ResNet, HRNet, OCR, and deep lab with 3 exceptions. For object detection, we use mainly efficient DET 70X and YOLO V3 BACSB. We use mean IOU visual accuracy for segmentation metrics while using IP50 and mean IP for detections. So performance is
we might have to wrap up there. Going a bit over time.
Oh, sorry.
Thank you. That's good. Yeah, if there's any questions, go to the paper, the poster presentations afterwards. Thank you very much.
Okay, sorry.
That's okay. Okay. Coming up next, we have Gabriel Miani. You have access to share now.
Yes, thank you very much. Can you hear me?
Yep, you're all good.
Thank you very much. So, good morning, everyone. I'm Gabriele Meoni. I'm from the Advanced Concept team. And in this work, we try to evaluate the use of heaven-based camera to land safely on the moon. So, first of all, what is an heaven-based camera? So, compared to the standard camera, heaven-based cameras are sensors where data pixel level are generated when the pixel illumination rises or falls beyond a certain threshold. So, if you compare to standard frame camera like here, where a new frame is generated with constant frame rate, here the computation is much more sparse because you have basically much more sparse data. So usually this is an interesting property because when processing on neuromorphic hardware, that requires low power consumption. And that's interesting for all the scenarios where you want to create like a lightweight and low power landing systems. So we evaluated the possibility to exploit the event flow generated by event-based camera to perform ventral visual based landings on the moon. So when I talk about ventral landing, I mean just perfect vertical descent. And we did it by using a time to contact. So what is time to contact is just basically a parameter equal to minus the ratio between the height, so the altitude, and the speed at a certain distance. And in previous work, they demonstrated that it's possible to use this parameter to control the spacecraft landing. So in particular, what we did, we considered a constant decrease in time to contact scenario. So basically time to contact has to be forced to be negative and constant during the landing. And to do that, we use a custom closed loop pipeline. In particular, the pipeline estimated divergence is basically 1 minus the time to contact from the event flow, and then set up basically a closed feedback loop to set up the breaking thrust of the spacecraft depending on the error. So the difference between the required time to contact and the one we measure. So the methodology is basically this one. We start from Pangu. That's basically a set of tools producing models of asteroids, planets, and also allows you to create images from them. And the Pangu API basically produce a new frames of the moon every time 10 milliseconds, depending on the spacecraft position. Then we use our converter to event-based data that works on the hypothesis just one event maximum per pixel is triggered between 2 Pangu frames, and time steps is assigned through a linear interpolation. That we use our approach that I will present in a second to estimate the divergence that's given to the controller to set up the breaking thrust, a true proportional controller. And the proportional controller acts on the Kraftal model that whose descent is described by using some differential equations. So the divergence approach is this one. So if you consider basically the event flow here, we cluster the events in max centroids. And how to use the centroids I will explain in a second to estimate the divergence. But if you make some mathematical passages, basically you arrive here and you can describe the divergence as a function of the position, a timestamp before, and the current position. So if you use some geometry and you know the position of 2 features basically on the ground, and the corresponding distance between centroids on the image on the camera plane, what you can do some true, basically simple geometry, considering two equivalent triangles. What you can see that the ratio between the altitude can be written as basically the distance over a couple of centroids over different times. And if you sum over the possible, basically a couple of clusters, you can estimate the divergence in this way. So we ran some experiments. In particular, we want to see the possibility of landing on the terrains with different features. So only craters, clusters for boulders, and sparse rock, and the terrains with very scarce features. And we consider a success criteria the landing as landing as a 50 meter, having a divergence higher than a safe value. Otherwise, what happens might be a crash. And also the velocity has to be negative, so it means that you're descending, just to be sure that your controller is stable. So results is basically those simulation is possible at the moment with the terrains with high features. The higher the feature, the better is for landing. Terrains with scarce feature also lead to crashes in some cases. So to sum up, we demonstrated landing is possible in some cases, depending on the features. And of course, there's room for improvement depending because of course we have very few spots to land. The control strategy is very simple, and so we want to work on it and improve it. Thank you for your attention. That's basically our presentation. That's our code. That please try it if you want. Thank you very much.
Thank you very much, Gabriele. Great presentation so far, everyone. Thank you. Next up, we have Andre for paper 4. Your access to share.
Okay. Just a second.
No worries.
Okay. Can you listen to me?
I can hear you.
Yeah.
You're sharing a screen.
Yes. Okay, can you see it now?
Yep, there we go.
Okay, cool. So I'm André Menezes, and I will be presenting a model-free reinforcement learning approach to dry stacking with irregular rocks. This work was developed in Institute for Systems and Robotics, Lisbon, along with Pedro Vicente and my supervisors, Alexandre Bernardino and Rodrigo Ventura. In situ resource utilization is a key aspect for an efficient human exploration of extraterrestrial environments. A cost-effective method for the construction of preliminary infrastructure is dry stacking with locally found unprocessed rocks. This method has been proven to produce long-lasting structures, as we can observe from some of the oldest human structures. And at the same time, it requires very little or no pre-processing time and energy. Our work focuses on learning this challenging task from scratch. We simulate an abstraction of the problem as the task of selecting a position to each object presented in a sequence on top of the currently built structure. The goal is to assemble a wall that approximates a target volume. In order to increase the diversity of the experience, we generate a large number of objects from which the sequences are sampled. We develop an agent to learn this task using the DQN algorithm. At each time step, the next object is presented. The perception of the agent is represented by elevation maps of an overhead view of the target volume and current structure, and the bottom view of the next object. The Q network estimates a value map corresponding to the expected return of placing the object on each position on the overhead view. This is used to select an action, represented by the position indexes on the overhead view. The object is then placed on top of the current structure, and the simulation is run until all objects stabilize. The agent is then rewarded with a metric based on the number of objects inside of the target volume and penalized by the distances between each object's original and current poses. To map the state to the values, we use a two-branch neural network architecture, where each branch is a fully convolutional module performing a pixel-wise feature extraction. We then compute the cross-correlation between the obtained features, which are mapped to the expected return using an additional fully convolutional module, phi out. Additionally, we match the dueling architecture by also estimating a separate state value from the target volume and current structure. We defined 3 reference levels of performance, selecting a random position inside of the target volume, and using the cross correlation to find the best fit in the current structure. And these are used to track the learning progress. So, starting with the random initialization, the agent quickly captures the goal of placing the object inside of the target volume. Then the heuristic is matched, which corresponds to learning a basic understanding of the environment dynamics. And finally, a strategy emerges, allowing the agent to outperform the heuristic. It learns to start an episode by placing the first objects on the boundary of the target area. This allows the following objects to be supported by an inwards sloping surface, which increases the overall stability of the structure. And this strategy is consistent with dry stacking theory. Here we can see some more examples of episodes with the learn policy along with the corresponding Q-network estimates. The key aspect of this work is that the policy is learned from scratch without requiring previously acquired models of the object or environment. Thank you. And if you have any questions or comments, feel free to reach out to me in the poster session.
Thank you very much, Andre. Up next, we have Marcus Swan. You're ready to go. Free to unmute and share your screen when you're ready.
Sorry, my Zoom disappeared. So
That's always a problem.
where did it go? Okay. Here, sorry, I'm gonna have to rejoin.
It's all right. Would we like to skip to the next one and come back to you?
That's fine with me.
Okay. I'll just quickly give Albert Garcia, are you ready to present?
Hello, yeah, can you hear me?
Yeah, I will make you co-host now. There we are.
All right, perfect.
Okay. So feel free to share a screen when you're ready.
Okay. Can you see now?
Looks good.
Perfect. All right. So, hello. My name is Albert Garcia, and I will now present our paper on SPNet, a 2D localization-oriented spacecraft pose estimation neural network. This work has been developed in combination between the Interdisciplinary Center for Security, Reliability, and Trust and LMO. In space missions, and especially during close proximity operations such as rendezvous and active debris removal, relative navigation systems require to estimate the relative position and orientation of a target object, known as pose. To this end, monocular visual cameras, which are space compliant due to their low power consumption and low mass, are good candidates for generating visual imagery. With these images, the pose of the target object, such as a spacecraft, can be estimated. So, our work focuses on uncooperative spacecrafts, which are characterized by not communicating any information either actively or passively. A common approach for monocular-based pose estimation is as follows. Given an image, a set of landmarks or key points on the spacecraft are predicted over the image. These are then corresponded to their respective 3D points over the 3D model of the spacecraft, and finally the pose is estimated through a PNP solver. This approach requires to have available 3D model of the target object, and it also sometimes involves a pose refinement process. Another approach consists in first performing object detection to localize the spacecraft in the image. And then the region of interest is cropped and used to estimate the pose, for instance, by direct regression through a CNN. This second approach generally makes use of a sophisticated object detection CNN, but our work aims to avoid using these techniques. To achieve this, we first started taking the widely used CNN architecture ResNet to directly regress the translation vector XYZ from the input image. This architecture has been extended to a UNet architecture, and also a transformation named DSNT is applied to the predicted heat map of this UNet architecture in order to estimate the center of the spacecraft in the image space, labeled as the vector UV. It is hypothesized that this additional task aids the precision of XYZ. Now we can take the output of coordinate UV as well as the Z coordinate, which represents the depth distance in meters to the target spacecraft, and define a process to compute a simple yet efficient square bounding box prediction. And to do this, we firstly scale Z with a hyperparameter K sub O, which depends on each target object. This scale value corresponds to the bounding box length and thus named BBL. Finally, taking this bounding box length and the predicted center coordinate in the image, we can easily define a square bounding box around the spacecraft. We can also easily augment these bounding boxes by perturbating their center, and this is what we have called centered augmentation, or CDA. Having computed this bounding box, we can pass it through another ResNet CNN, which directly regresses the relative orientation in a quaternion form. All in all, here is a diagram of the overall proposed LSPNet architecture. And as a last modification, we have also proposed to concatenate all the last feature maps from the localization CNN into this region of interest, and we have named this heat map concatenation, or HC. So in order to validate LSPNet, several experiments have been conducted using the grayscale synthetic images of the speed dataset, and a first ablation study has been performed in order to see the impact of including this additional task of predicting these UV coordinates corresponding to the right architecture. And the results show that UV, in fact, aids translation estimation. A more extensive ablation study has also been performed in order to compare how to initialize the orientation CNN, the inclusion of HC, and the inclusion of CDA. So, having found the best implementation for LSPNet, a comparison with the state-of-the-art on speed has also been done. LSPNet achieves better position results, but not better orientation results compared to the spacecraft pose network, which is a CNN proposed in addition to the release of the speed dataset. Also, LSPNet has been localized on the latest spacecraft pose estimation challenge. This competition involved around 40 teams and challenged the teams to perform pose estimation over the speed dataset. LSPNet positions itself at the 8th rank on both translation and orientation errors. But also it is worth remarking that team numbers 1 to 10, as well as the baseline, they involved in some way 3D models, pose refinement, or an object detection CNN. So to conclude, we have seen that LSPNet can predict simple yet efficient square bounding boxes. We have also seen that the UV aids the position estimation. And finally, we could say that LSPNet is a rather simple model, but still competes with the state-of-the-art on speed dataset. Thank you for your time.
Thank you very much, Albert. Another great presentation. If we can stop sharing now, we're going to jump back to Michael Swan for paper number 5. We've given you permissions.
Yep.
Excellent.
1 second.
Your Zoom's working this time.
Seems to be.
Good.
Okay. Let's see. Okay, can you see it?
Yep, looks like you're good to go.
All right. So, hi, my name is Michael Swan, and this is our presentation of AI for Mars, a data set for terrain. Oh, sorry.
Just letting you know, we're seeing your presenter view.
Oh no.
Yeah.
Okay. Okay. Well, we'll go without that. Okay. So yeah, so I'm presenting this data set for terrain-aware autonomous driving on Mars. And I'm a student at the University of Southern California, and I'm also currently, as a master's student, and I'm also currently interning at NASA JPL, which is where this work was conducted. So to just justify this work, why do we need better autonomy? So lunar rovers were able to move much faster in the past, and compared to, say, the Curiosity rover. For example, the Apollo lunar roving vehicle was able to go about 22 kilometers without stopping, while the Curiosity rover has taken over a few 9 years to do almost the same, to do less distance actually. So what do we need in order to make better autonomy happen? First, we need a simple mobility system, and second, we need intelligent perception and planning. So to further justify this, let's take a look at the efficient and safe autonomy. So existing hazard detection depends on stereo vision, and it cannot identify non-geometric hazards. It's brittle. And all Mars rovers except for Sojourner were nearly or permanently embedded in sand. So what we can do about this is we can take the human view of the terrain and try to do rover autonomy using that terrain. And this is the basis for the AI4Mars dataset. And so this dataset we collected through the Zooniverse platform, which is a tool for crowdsourced data collection. And we had thousands of volunteers who helped us collect over 400,000 labels on 35,000 images from Curiosity, Opportunity, and Spirit. These labels, when I say label, it refers to all the pixels in a single image which were labeled by a single person. It does not refer to like a single polygonal annotation. Yeah, this was a very successful effort. One other question that often comes up is why do we have so many labels with this many images? And sort of the answer is sort of twofold. One is you need more labels when you have volunteer scientists or citizen scientists, just to ensure that you get good quality labels for each image. And another was basically there was so much supply that we had an issue providing enough data for everyone to label. And so sometimes people did a little bit extra labeling. So what terrain classes were actually being labeled? What is actually occurring here? In order to come up with some basis for terrain-aware autonomy, we asked rover planners at NASA JPL, and we asked them what is important for driving the rover. And they gave us these 4 classes, which is soil, sand, bedrock, and big rock. One thing to note is big rock is about 2% of our data set, and that makes things a little bit more challenging. Part of this could be just due to the sort of the terrain makeup on Mars. Another part could be sort of the ambiguity of the data class, since it's people have difficulty understanding what is 30 meters or what is 5 meters in size. In order to experiment with this data set and validate that it was useful and working for us, we tested on the DeepLab v3 Plus framework using ResNet 101 architecture and ImageNet background. And we were able to get decent inferences from that, which I'll show next. Before I go there, in order to validate our training, we also needed to collect a test data set because the citizen scientist labels, they have some level of accuracy that we need to verify. And so we had to collect a expert data set. So with that expert data set, we were able to get a very high accuracy and with testing against that data set. And not to say that all the work is done here, there's still quite a bit more because there's still the challenge of generalizability. So in conclusion, we have this data set has over 400,000 labels. It's the first Mars data set of this size. And we had pretty good results in the data. And so we really want more help in order to make this happen in the future and make safe, efficient, and long-range autonomy available on other planets. You can find it on data.nasa.gov, and if you search for AI4Mars. Thank you.
Thanks very much, Michael. I'm glad to see we got your technical issues worked on the end. Up next, we have Roshan. You still available? Yep. Excellent.
Yeah.
You should have permissions now. Do you want to try and share your screen?
Sure. 1 second.
Your audio is perfect, by the way. Excellent. And there's your video. Yep.
Okay. Hi. So our work is MarsCat. It's a spatial channel attention guided network for Mars rover classification. My co-authors are Anirudh and Praveen, and we're from BITS Pilani in India. So quick agenda, I'll be introducing the topic, providing some motivation, proposing our method, showing you some results, and if we have time, maybe extending it to the perseverance data, whatever work we've done. So as human exploration pushes into the galaxy and we start to collect more on-planet surface data, classification of images becomes interesting and important, and it's challenging because of differences in hue, quality, illumination, clarity. To that end, we use the MSL surface data set from the Curiosity rover. It consists of 6,700-ish images from the Mars surface environment collected by 3 instruments from NASA's rover. These images are shot with different cameras of different focal lengths, resolutions, and fields of view. So I'll just jump right into it. As I mentioned earlier, our task is simple in the sense it's a multi-class classification problem. The input to our network is a bunch of RGB images, and the output is a class, depending on the 24 classes available in the dataset. So given an image, we extract the features with the backbone, and this serves as the first stage of the network. And now we come to the attention blocks, and I guess that's where the slightly interesting part comes. So visual attention is known to basically improve the descriptive ability of features by focusing on important features and ignoring the rest. And so in order to account for these challenging variations during image capture, we basically attempt to enrich these features based on 2 different attention mechanisms, which is the channel attention block and the spatial attention block. So concretely, the backbone features are refined using this channel attention block. And what it does is it attempts to learn the inter-channel dependencies. So if we have C channels, it learns a filter WC of dimension C, which has the important information in each channel stored. And so this kind of guides the network about what to look for in these backbone features. We then pass the channel refined features to the spatial attention block. The spatial attention block learns obviously a spatial filter. And these filters allow the network to basically learn where to look for important information. So as I mentioned earlier, the Mars images have a lot of spatial variations in terms of background and angle of capture. So it's important to have an idea of robust spatial features. And so it generates a filter for each height and width of each image, so across each spatial dimension. Finally, we have a multi-layer perceptron to generate the predictions. Just a quick note. So this is the standard ResNet 50 architecture. What we did was we didn't train, we only unfroze the last Res5 layer. And so our model uses relatively lower number of parameters. Why we do this is because we want the model to be relatively inexpensive during training, but still accurate at deployment. And I guess it's kind of significant because with an increasing number of classes, we may want to fine tune further on the data set. So it helps that way. I'll just quickly take you through the experimental results. So on the MSL dataset, we get state of the art on the test set. You can examine the class-wise accuracies on your right-hand side on table 2. The baseline overfits on classes like Scoop. The precision, although the accuracy is high, 100%, the precision is low, and our model does a better job of generalizing. And so In classes like Chem Inlet Open, we actually do a lot better. Yeah, a couple of the classes are visually very similar, so hard to classify, but essentially it performs better. So the ablation, so first we ran the standard ResNet 50 with the 5th stage unfrozen, and we get an accuracy of 76.16%. We then only use our spatial attention block, and we get a performance of 76.86%. Kind of surprising, because we initially thought that we'd get a better performance boost with the spatial attention. But we hypothesized that the ResNet backbone is able to kind of explain the spatial variations. And so what we did was we ran the baseline without.
Sorry, Sean.
Yeah.
Sorry, Sean. Thank you so much for your presentation. Just running out of time. Might have to move on here.
Sure.
So take us to the post presentation stuff.
In the poster. Yeah, sure.
Sounds great. Thank you very much. Up next, we have Bo Chen.
Yes.
You're here. Yeah. Good to see you, Bo.
Thank you, Luke. Yeah, I'm trying to share my screen.
Yeah. It's coming through.
Can you see my screen?
Yeah, there we go. Good to go.
Okay. Thank you. Hello, everyone. My name is Bo Chen. In this work, I'm going to talk about a recent AI competition, the Kelvin Spot Geo Challenge, which was co-organized by Interest Solution and the Advanced Concept team from ESA. So what is Spot Geo? In short, the task of Spot Geo is to detect satellites in or near the geostationary orbit with images obtained on the ground. It is an important task because ground-based monitoring of space objects is a crucial aspect for achieving space situational awareness. However, detecting objects from the ground is very challenging. A fundamental reason behind the difficulty is the extreme distance between the camera and the target object. In our case, one image pixel is equivalent to 800 meters of arc length at the geo orbit. Other nuisance factors such as weather, light pollution, sensor noise, etc. also contributed to the difficulty of this task. And another difficulty comes from the lack of publicly available data sets for the research community to develop and test machine learning algorithms for this task. So by organizing the Spot Geo Challenge, we hope to first establish to what extent images coming from a ground-based camera can be used to detect geosatellites. We also aim to address the lack of publicly available data sets by releasing our developed data sets for this challenge. So to develop the Spot Geo dataset, we employ a low-cost CMOS sensor to capture the night sky. Objects at the geo orbit, they move synchronously as the Earth's rotation. So they will appear as point-like objects in the image. On the other hand, stars will appear as streaks due to their constant sidereal motion relative to Earth. These geo objects could be dim small points, which can easily cause false positive and false negative detections. To make the problem more feasible, we employ multi-frame based detection techniques by capturing sequences of 5 images. For each sequence, for each frame, we firstly set the camera still for exposure time of 40 seconds. And after we obtain each image, we slightly rotate the camera to observe a different field of view, while making sure that there is a significant overlapping with the previous view. We repeat this process until we get the full sequence. So an important feature of this capturing process is that the rotations between frames are identical, which means if we stack the 5 images together, the locations of a geo object should have a line structure. This is an important constraint which is to be exploited. For example, if you have detection results like on the left image, you can utilize this prior to easily filter out false positives or interpolate false negatives. For evaluation metrics, all participants are ranked primarily by the 1 minus F1 scores. We also use the prediction MSE as a tiebreaker. To calculate the F1 scores, we first perform a one-to-one matching between the predictions and the ground truth locations by minimizing the sum of the truncated distances of each match pair. We then use a threshold tau to determine whether each match is a true or false positive. We have attracted a total of 33 teams from all over the world. This list shows the top 10 teams ranked by their 1 minus F1 score. In conclusion, the first and foremost message we learned from this competition is that images obtained from ground-based cameras can be used to detect satellites fairly well, with a F1 score as high as 95%. We have also summarized a popular 3-step pipelines which work well for most participants, which consists of first pre-processing the images, and second detect the potential objects with either a neural network or some filter-based techniques, and third post-processing utilizing the temporal structure to refine the test result, the detection result. We have made our dataset available on Zenodo as well as the toolkit. Feel free to play with the dataset and advance the techniques for spot geo. Thank you.
Thanks very much for your talk, Bo. Great as always. And you will, yes, you are. Okay.
Yes.
So this is our last spotlight presentation. Take it away when you're ready.
Thank you. Can you see my screen?
Yeah.
So hello and welcome to the CVPR 2021 oral presentation for AI4Space workshop. My name is Anne Mergy and we are going to talk about vision-based neural scene representations for spacecraft. The spacecraft's capacity to be aware of its position relative to another object is essential for close proximity operations. For instance, as shown on the pictures, accurate formation flying and docking during the PRISMA mission, orbital debris removal during ED orbit, or on-orbit monitoring for maintenance of satellites. Current satellites carry specific tools to measure the surrounding environment, such as radio frequency modules or LiDAR systems. This work considers the use of a single monocular camera to reconstruct a full-colored three-dimensional model of a targeting object, as shown on the bottom part of this slide. The resulting vision-based system is potentially low-cost and mainly passive when compared to the current solutions. The objective of this work is to study and compare the performance of neural scene representations to infer three-dimensional scenes from optical images. So far, the use of 3D CNN to predict 3D voxel RGB grids to represent new views of a scene was a successful approach but had bad scaling properties. Neural radiance fields were introduced last year by Mildenhall et al. They take as input sparsely sampled images of a scene along with their corresponding camera poses and use a multi-layer perceptron to output a color value and a volume density corresponding to the visual rendering of the object at this specified position. Taking into account the direction of the ray allows to render view-dependent effect on the material of the object. Color and density values are then computed along the ray from the camera, and the scene representation is finally optimized considering output prediction and ground truth values. However, in space, obtaining the pose from optical images of spacecraft is not trivial when they are uncooperative. Generative radiance fields introduced by Schwartz et al. Use an adversarial training scheme to train a nerve from a set of unposed images and learn the 3D representation of the scene. The abstraction of the pose is possible thanks to the discriminator that forces the generator to represent the probabilistic distribution of the training dataset. The generator of the graph is composed of a radiance field conditioned on several parameters. It takes as input a requested pose that will be used during inference to synthesize an image representation of the scene from that viewpoint. We are curious to know if we can estimate the depth of objects in space with and without the information of the pose. We want to quantify the rendering performance of graph compared to NERF, even though the information of the pose is missing. For that, we created a synthetic dataset containing densely sampled scenes of 100 images of ESMOS satellite, which is covered with a highly reflective material. We used a single directional light source, a black background, and a camera at 10 meters with viewpoints uniformly sampled on a sphere around the object. The figure shows generated images of NERF and graph on unseen viewpoints. NERF has the ability to generate realistic sharp images with better quality results regarding lighting conditions and view-dependent effects. Graph generates good quality results, although the information of the pose was not here during the training. It also renders an image even when the scene is dark. Quantitative results confirm that NERF leads to better rendering with a higher PSNR and a higher SSIM values. Both models lead to the same intersection over union. They have the same completeness for object detection. We can see here depth estimation by both models on unseen viewpoints. And we see that graph leads to a better depth prediction. Also, the pose is not precise. It's slightly shifted compared to round truth. So it is possible to learn a 3D representation of a spacecraft from RGB images, whether the pose is or is not known. Using an adversarial training scheme when the pose information is not available leads to achieving better results in darker conditions. And it also leads to a less accurate rendering of the pose as it was not used during the training. The main limitation of this work being the synthetic dataset, the next step would be to test and adapt those methods to a real-life scenario. That is why we also studied a scenario with fewer images used during the training, which I can tell you more about during the poster session. Thank you for your attention. And here is a part of our bibliography for reference.
Thank you very much, Anne. And thank you to everyone who presented. We'll now turn back over to TJ to guide us into the next section.
Yep, thanks for Luke for handling the spotlight. Thanks to all the presenters as well. As mentioned earlier, we should go into the breakout rooms. You should be able to join the breakout room yourself without the host to assign you. Kindly, for the presenters, go to the correct room based on your paper number. And yes, you can all start discussing now. We have about 20 minutes, and then I'll send a message to everyone to come back so that we can proceed to the next segment, which is the award segment. So, yep, let's split into the breakout rooms and talk.
Back again.
Good to see people managing to come back when they don't have the button to do it. So good.
Hello, everyone. I think it felt like the poster session was too quick, but you know, I saw a lot of active discussions. But you know, after all, this is a virtual workshop. People do get tired if you spend too much time in front of the computer. So I'd like to move into the next segment, but I am waiting for Marcus. Is Marcus here?
Yes, I know what you're waiting for. I'm doing it.
Okay. So as Marcus is doing that, let me share my screen so that we can move on to the next segment. Hang on, please bear with me while I find my slides. Sorry, everyone. Yeah, I'll be right with you. Sorry. Almost done. All right, here we go. Okay, the moment we've all been waiting for. Firstly, some statistics about the workshop. We had 32 paper submissions. Honestly, the organizing team felt thankful for this many contributions. When we submitted the proposal to CVPR workshop committee, we weren't sure whether this topic is the right one for this this community, CVPR community. I remember one of the criteria we have to justify in the proposal is what were the related workshops in CVPR in the past 5 years. And I remember checking not just CVPR, but ECCV, ICCV, ACCV, all the relevant computer vision conferences, and none were on space, none were on this topic. So we were a bit unsure of whether this is the right one. But given that we had 32 submissions, it's a big sign that, yeah, this is something that's worth pursuing, and hopefully we can continue doing into the future. We had 33 reviewers, all experts in their field of study, of course, all relevant to AI and computer vision and machine learning in general as well. We thank them for their expert opinion and generous time. Reviewing was double blind, and each paper got at least 2 review reports. Okay, decisions were made by meta reviewers under the condition of completely no conflicts of interest. And out of 32 papers, 17 got accepted. Okay, so today, did I open the right set of slides? Yeah, we've got block B here. Now, Best Paper Finalist Award and Best Paper Award both were presented yesterday already in block A. So if there was no information leaked from block A, this should still come as a surprise to the winners. But today the new award is Best Presentation Award for block B. So this is based on your performance earlier in the spotlight. Okay, so we would like to thank our sponsors again. Without them, these awards, indeed, this workshop wouldn't be possible. So Draper Labs, Black Swan, and Australian Space Agency. Okay, Base Paper Finalist Award goes to AI for Mars, a data set for terrain-aware autonomous driving on Mars. So Michael is here today, who presented the paper on behalf of his colleagues from JPL. Congratulations. Sorry, I have those. Okay, so why do we think this was, why did the reviewers and the meta reviewers thought that this was a Best Paper Finalist Award? The biggest data set released from another planet so far. That just sums it up. All right. I think the scientific value of this work is definitely there, and autonomous driving, the concept itself, you know, it's a hot topic currently. Billions of dollars being thrown in. Allowing this to be done on another planet is you know, has obvious scientific value, as mentioned earlier. So congratulations, Michael. Would you like to say something?
I just want to say thank you. It's actually really unexpected for me, but I will definitely pass it on to the team and tell them the good news. Yeah, I want more people to be able to use autonomy on Mars and other planets, and I think this is one of the first one of the early steps. So
cool. And there was, so I presume that means that there was no information leaked from last night.
I heard nothing.
Perfect. So congratulations again, and Best Paper Award goes to this paper here, Improving Astronomy Image Quality Through Real-Time Wavefront Estimation, which was already presented in Block A yesterday. David, the first author, was there to tell us about this fantastic work. Why did we think this was worthy of the Best Paper Award? I think summarizing using my own words, it's a very unique application of machine learning, particularly convolutional neural networks, not in detecting things in the scene or segmenting the semantic labels, but in improving astronomy, improving imaging in astronomy, so to help further science. So congratulations to David and his team from Stanford and Lawrence Livermore National Labs. Best Presentation Award in Block B goes to Monocular Post-Estimation Case Study, the Hayabusa 2 Minerva 2 deployment. And Andrew was here to present that paper today. Andrew, are you still with us?
Get that same buzz again.
Yeah, same buzz.
I'm sorry. Okay. Thank you very much. From a more global perspective of this whole workshop, I'm very thankful. I think I came from perhaps the smallest team here when presenting this. So the feedback from the reviewers especially, it was really phenomenal. And it was just absolutely wonderful getting this opportunity. It's really, really good to be able to expose your work and get some good insight. So thank you.
Perfect. And we have a special thing as well today. I'm frantically preparing my slides because this is all decided just a few minutes ago. We couldn't decide between this work and the next work. So I think we have enough left over from our sponsors cash to award another Best Presentation Award, which goes to vision-based neural scene representation for spacecraft, which Anne presented on behalf of the team. Anne, are you still here?
I am. Thank you so much. And thank you for the interest. And thank you to Gurvan, the other first co-author, and Dawa and Dario as well.
Cool. With that, let's congratulations to the team. With that, let's move to the end of the workshop proper. Thank you very much to everyone. Thank you to the team, Luca, Marius, Clinton, Marcus, Pablo. Most importantly, actually, Bo and Luke. Without them, this event wouldn't be running so smoothly over the internet. Okay, so hopefully there will be a next AI4Space workshop, and hopefully it's going to be a physical one so that we can see each other, you know, in a nice location in a conference room. Thank you very much for your contributions and participation. Have a great day. See you.
It has also some shout outs for TJ, who was the head organizer of this. Did an excellent job in yeah, keeping everything smooth and working out in the end. So thanks.
Thank you. The trick is a lot of nagging.
But it was effective. It was good.
Okay. Thank you, everyone. See ya. Bye.